Welcome. This is a presentation on suffix trees presented by Lawrence Oakes for the class COT 5405. Today we'll be talking specifically about constructing them in linear time and some of their applications. Of course, we'll start with an introduction to suffix trees, beginning with the formal definition. A suffix tree is a compressed trie in which every suffix of a string S is represented. They are particularly useful for fast implementations on many string operations, two of which we will discuss later in the presentation. As an example to demonstrate what a suffix tree looks like, we will use the string banana, where the null character is the termination character. The following are all of the possible suffixes of banana. If we consider all of the suffixes as individual words, we can build the following standard trie. As shown on the left, on the right, we have a compressed trie, which is obtained from the standard trie by joining all the chains of single nodes. The nodes of a compressed trie, or suffix tree, can be stored by storing the index ranges at the nodes. We will now move on to presenting an algorithm to construct a suffix tree in linear time. While Peter Wiener was the first to demonstrate that suffix trees could be constructed in linear time, it is Ukkonen's method that is equally as fast, yet requires far less space in practice than Wiener's method, and is also conceptually easier to understand. For these reasons, it is most often chosen for problems requiring the construction of a suffix tree, and so it is the one that we'll be learning about. So Ukkonen published his algorithm to construct a suffix tree in linear time in 1995. Compared to Peter Wiener, it saved space but was also simpler in description, proof, and time analysis. It begins with an implicit suffix tree containing the first character of the string and continues to step through the string, adding successive characters until the tree is completely built. This order of adding characters from left to right gives the algorithm its on-line property, which can be useful in some situations. In the following slides, I will attempt to describe the algorithm by first showing how it works with a very simple string and then extending it to the full algorithm, first with simple repetitions and then with suffix links. So we will first start with a very simple string with no repeated characters, which is ABC. The algorithm works in steps from left to right. There is one step for every character of the string. Each step might involve more than one individual operation, but we will see at the end that the total number of operations is O of n. So we start from the left and first insert only the single character A by creating an edge from the root node on the left to a leaf and labeling it as 0, hashtag, where the hashtag represents the current end of the string. I use the symbol hashtag to mean the current end, which right now is at position 1, right after A. So we have an initial tree, which you can see, and it means that we are just using the substring A. Now we will progress to position 2, which is right after B. Our goal at each step is to insert all suffixes up to the current position. We do this by expanding the existing A edge to AB, and inserting one new edge for B. In our representation, you can see what this looks like. And we observe two things. The edge representation for AB is the same as it used to be in the initial tree, from 0 to current end. Its meaning has automatically changed because we updated the current position, the hashtag, from 1 to 2. Each edge consumes O of 1 space because it consists of only 2 pointers into the text, regardless of how many characters it represents. Next, we increment the position again and update the tree by appending a C to every existing edge and inserting one new edge for the new suffix C. In our representation, this looks like the tree on the left, and it means the tree on the right, which you can see with the actual letters of the string. We can observe that the tree is the correct suffix tree up to the current position after each step. There are as many steps as there are characters in the text, and the amount of work in each step is O of 1, because all existing edges are updated automatically by incrementing the current position, and inserting the one new edge for the final character can be done in O of 1 time. Hence, for a string of length n, only O of n time is required. Now, of course, this works so nicely only because our string doesn't contain any repetitions. We are now going to look at a more realistic string, which you can see is ABC, ABX, ABCD. It starts with ABC as in the previous example, and then AB is repeated, followed by X, and then ABC is repeated, followed by D. After the first three steps, you can see we have the exact same tree from the previous example. So we will move on to position 4. When we move the current position to position 4, this implicitly updates all existing edges to the tree you can see. And finally, we need to insert the final suffix of the current step, A, at the root. But before we do this, we need to introduce two more variables in addition to the current position, which of course have been there the entire time, but we haven't used them so far. The first is the active point, which is a triple that includes active node, active edge, and active length. The second variable is the remainder, which is an integer indicating how many new suffixes we need to insert. The exact meaning of these two will become clear soon, but for now we'll just say, in the simple ABC example, the active point was always root, null, and 0. In other words, the active node was the root node, the active edge was specified as the null character, and the active length was 0. The effect of this was that the one new edge that we inserted in every step was inserted at the root node as a freshly created edge. We will see soon why a triple is necessary to represent this information. The remainder was also set to 1 at the beginning of each step. The meaning of this was that at the number of suffixes we had to actively insert at the end of each step was 1, which was always just the final character. Now this is going to change. When we insert a final character A at the root, we notice there is already an outgoing edge starting with A, specifically ABCA. Here is what we do in such a case. We will not insert a fresh edge for current position at the root node. Instead, we will simply notice that a suffix A is already in our tree. It ends in the middle of a longer edge, but we're not bothered by that. We just leave things the way that they are. We set the active point to root A1. That means that the active point is now somewhere in the middle of the outgoing edge of the root node that starts with A, specifically after position 1 on that edge. We notice that the edge is specified simply by its first character A. That suffices because there can only be one edge starting with any particular character. We also increment remainder so that at the beginning of the next step it will be 2. Observe that when the final suffix we need to insert is found to exist in the tree already, the tree itself is not changed at all. We only update the active point and the remainder. The tree is then not an accurate representation of the suffix tree up to the current position anymore, but it contains all the suffixes, because the final suffix A is contained implicitly. Hence, apart from updating the variables, which are all of fixed length, so this is an O of 1 operation, there was no work done in this step. For step 5, we update the current position to 5. This automatically updates the tree to the one you can see. And because the remainder is 2, we need to insert 2 final suffixes of the current position AB and B. This is essentially because the A suffix from the previous step has never been properly inserted, so it has remained, and since we have progressed one step, it has now gone from A to AB. And we also need to insert the new final edge B. In practice, this means that we go to the active point, which points to the A on what is now the ABCAB edge on the top, and insert the current final character B. But again, it turns out that B is also already present on the same edge. So again, we do not change the tree. We simply update the active point to root A2 Same node and edge as before, but we now point behind the b. And increment the remainder to 3 because we still have not properly inserted the final edge from the previous step, and we don't insert the current final edge either. To be clear, we had to insert AB and B in the current step, but because AB was already found, we update the active point and did not even attempt to insert B. Why is that? Because if AB is in the tree, then we know every suffix of it, including B, must be in the tree as well. Perhaps only implicitly, but it must be there because of the way that we have built the tree so far. We will proceed to step 6 by incrementing the current position. The tree is automatically updated to the following, and because the remainder is 3, we have to insert A, BX, BX, and X. The active point tells us where AB ends, so we only need to jump there and insert the X. Indeed, X is not there yet, so we split the ABC ABX edge and insert an internal node, which you can see in the tree at the bottom. The edge representations are still pointers into the text, so splitting and inserting an internal node can be done in O of 1 time. So we have dealt with ABX and decrement remainder to 2. Now we need to insert the next remaining suffix BX, but before we do that, we need to update the active point. The rule for this, after splitting and inserting an edge, will be called Rule 1, and it applies whenever the active node is the root. Here is Rule 1. After inserting from a root, active node remains root, active edge is set to the first character of the new suffix we need to insert, in other words B, and the active length is reduced by 1. Hence, the new active point, root B1, indicates that the next insert has to be made at the BCABX edge, behind 1 character, in other words behind B. We can identify that the insertion point in O of 1 time and check whether X is already present or not. If it was present, we would end the current step and leave everything the way it is. But X is not present, so we insert it by splitting the edge. And you can see that following the blue line on the tree at the bottom. Again, this took O of 1 time, and we update the remainder to 1 and the active point to root x 0 as Rule 1 states. But there's one more thing we need to do. We'll call this Rule 2. If we split an edge and insert a new node, and if that is not the first node created during the current step, we connect the previously inserted node and the new node through a special pointer called a suffix link. We will later see why that's useful. Here is what we get. The suffix link is represented as a dotted edge. We will still need to insert the final suffix of the current step X. Since the active link component of the active node has fallen to 0, the final insert is made at the root directly. Since there is no outgoing edge at the root node starting with X, we will insert a new edge. As we can see in the current step, all remaining inserts were made. So we will proceed to step 7 by setting the current position to 7, which automatically appends the next character A to all leaf edges as always. Then we attempt to insert the new final character to the active point, or the root, and find that it is there already. So we end the current step without inserting anything and update the active point to root A1. In step 8, we set the current position to 8 and we append B. As seen before, this only means that we update the active point to root A2 and increment remainder without doing anything else, because B is already present. However, we notice, in O of 1 time, that the active point is now at the end of an edge. We reflect this by resetting it to node 1, null, 0. Here I use node 1 to refer to the internal node the AB edge ends at. Then, in step 9, we need to insert C, and this will help us understand the final trick. And that is the second extension, which is suffix links. So as always, The current step update appends C automatically to the leaf edges, and we go to the active point to see if we can insert C. It turns out C already exists at that edge, which you can see here. So we set the active point to node 1, C1, and we increment the remainder and do nothing else. Now in step 10, the remainder is 4, and so first we need to insert A, B, C, D, which remains from the 3 steps ago, by inserting D at the active point. Attempting to insert D at the active point causes an edge split in O of 1 time, and you can see that in blue. The active node, from which the split is initiated, is marked in red. So here's the final rule, Rule 3. After splitting an edge from an active node that is not the root node, we will follow the suffix link going out of that node. If there is any, we reset the active node to the node it points to. If there is no suffix link, we set the active node to the root. Active edge and active length will remain unchanged. So the active node is now node 2, C1, and node 2 is marked in red here. Since the insertion of A, B, C, D is complete, we decrement remainder to 3 and consider the next remaining suffix of the current step, B, C, D. Rule 3 has set the active point to just the right node and edge, so inserting BCD can be done by simply inserting its final character D at the active point. Doing this causes another edge split, and because of Rule 2, we must create a suffix link from the previously inserted node to the new one. And you can see that link created by the dashed line. We can observe that the suffix links enable us to reset the active point so we can make the next remaining insert at O of 1 time. Look at the graph to confirm that indeed the node at label AB is linked to the node at B, and the node at ABC is linked to BC. The current step is not finished yet. Remainder is now 2, and we need to follow Rule 3 to reset the active point again. Since the current active node, in red, has no suffix link, we reset to the root. The active point is now root C1. Hence, the next insert occurs at the one outgoing edge of the root node whose label starts with C, which is CAB, XAB, CD, behind the first character, in other words behind C. This causes yet another split, as shown in blue here. And since this involves the creation of a new internal node, we follow Rule 2 and set the suffix link from the previously created internal node. But this remainder can be set to 1, and since the active node is root, we use Rule 1 to update the active point to root D0. This means that the final insert of the current step is to insert a single D at the root, and that is shown in blue. This was the final step, and we are complete in constructing our suffix tree. There are a number of final observations we can make. In each step, we move the current position forward by 1. This automatically updates all leaf nodes in O of 1 time. But it does not deal with, first, any suffixes remaining from the previous steps, and second, with the one final character of the current step. Remainder tells us how many additional inserts we need to make. These inserts correspond 1-to-1 to the final suffixes of the string that ends at the current position. We consider one after the other and make the insert. It's important to note that each insert is done in O of 1 time, since the active point tells us exactly where to go, and we need to add only one single character at the active point. Why is that? Because the other characters are contained implicitly. After each such insert, we decrement the remainder and follow the suffix link if there is any. If not, we go to the root, as we described in Rule 3. If we are at the root already, then we modify the active point as we discussed in Rule 1. In any case, it takes only O of one time. If during one of these inserts we find that the character we want to insert is already there, we don't do anything and end the current step, even if the remainder is greater than 0. The reason is that any inserts that remain will be suffixes of the one we just tried to make. Hence, they are all implicit in the current tree. The fact that remainder is greater than 0 makes sure we deal with the remaining suffixes later. What if, at the end of the algorithm, remainder is greater than 0? This will be the case whenever the end of a text is a substring that occurred somewhere before. In that case, we must append one extra character at the end of the string that has not occurred before. In the literature, usually the $sign is used as the symbol for that. Why does this matter? If later we use the completed suffix tree to search the suffixes, we must accept that matches only if they end at a leaf. Otherwise, we would get a lot of spurious matches because there are many strings implicitly contained in the trees that are not actual suffixes of the main string. Forcing remainder to be 0 at the end is essentially a way to ensure that all suffixes end at a leaf node. However, if we want to use the tree to search for general substrings, not only suffixes of the main string, then the final step is indeed not required. So, what is the complexity of the entire algorithm? If the text is n characters in length, there are obviously n steps, or n plus 1 if we use the $sign. In each step, we either do nothing other than updating the variables, or we make the remainder inserts, which each take O of one time. Since remainder indicates how many times we have done nothing in the previous steps and is decremented for every insert that we make now, the total number of times we do something is exactly n, or n plus 1 in the case of the $sign. Hence, the total time complexity is O of n. Now we will discuss two applications of suffix trees, that is substring matching and the longest repeated substring. Starting with substring matching, given a text string and pattern string, we want to check if the pattern exists in the text or not. This is particularly useful in applications, for example, like DNA, in which you need to look for a small pattern in a large text. Once we have a suffix tree built for the given text, we traverse the suffix tree from root to leaf against the characters in the pattern. If we fall off the tree, quote unquote, during traversal, then the pattern does not exist in the text. Otherwise, there is a path from the root to leaf or somewhere in between, so we have a match. An example of this can be seen here. If we have the text XAB $, we can see that on the left, BXA is a substring, and all the way on the right, XABX is also a substring. But if we try to search for the pattern ABC, we will fall off the tree, and we can see that that pattern does not exist in the text. For our next application, we have longest repeated substring. To do this, we traverse the tree to find the deepest internal node. While longer substrings exist, we know they are not repeated because they have no internal node down the tree. Why does this work? Well, in a suffix tree, one node can't have more than one outgoing edge starting with the same character. So if repeated, they will share the same path, and that path will go through one or more internal nodes down the tree. We can see an example of this application here. The longest repeated substring is ABABA, which you can see has the deepest internal node at a height of 3. Thank you for listening, and I hope you learned something about suffix trees today.